Welcome to Definite versus Indefinite Integrals by Conceptual Calculus. We were first introduced to integration as finding the area between a function and the horizontal axis from some starting point to some ending point. This is called a definite integral because we know definitely where we are starting and where we are stopping. We could find the value of the area by using limits of Riemann sums, which was a long, tedious mess. Then we met the fundamental theorem of calculus and learned that we could find the value of this definite integral by using an antiderivative, which is a derivative done backwards. That was great because it meant we could get away from the Riemann sums. It does mean that we have to learn how to do differentiation backwards, but if it gets us away from the Riemann sums, then it's worth it, I think. That's when we meet the indefinite integral. It is called indefinite because we do not have limits of integration, those little numbers that tell us where to start and stop when we add up the rectangles. The indefinite integral is just the antiderivative. It does not represent area because you can't have area without boundaries on the region. There is another thing that is indefinite about this kind of integral, the plus c on the end. C represents a constant number, but we don't have a specific value to use for c, so that's kind of indefinite. The indefinite integral needs a plus c, and the definite integral does not. Let's look at why that is. First, we look at the derivative of a few functions. What is the derivative of x cubed? Remember the power rule. We bring down the exponent and use it as a coefficient, and subtract 1 from the exponent, so we get 3x squared. Now, what's the derivative of x cubed plus 6? The derivative of x cubed is 3x squared, and the derivative of the 6 is 0, so the total is 3x squared. What about x cubed minus 4? Its derivative is also 3x squared. Now we want to go the other way. We have a derivative of 3x squared, and we want the original function. It could be x cubed plus 6, x cubed minus 4, or any similar function. We represent all of these possibilities by writing x cubed plus c, where c stands for a constant number. Notice that c cannot be a function of x. It can't be the sine of x or the square root of x or anything like that. It has to be a constant number because its derivative has to be 0. This gives us the antiderivative, also known as the indefinite integral. Now let's look at a definite integral involving 3x squared. Find the area between the curve y equals 3x squared and the y-axis from x equals 1 to x equals 2. When possible, I always start with an estimate. That helps me know whether I've gotten the right answer at the end. We can estimate the area from this graph. The lower part of the region is a rectangle with a base of 1 and a height of 3, so its area is 3. The upper part of the region is approximately triangular. It is not exactly a triangle, because triangles have straight sides and the parabola is a curve, but the region is close enough to triangular that we can use it as an estimate. The triangle has a base of 1. The vertical dimension goes from 3 to 12, so the height is 9. This gives an area of 4.5 for the triangle. Adding the areas of the rectangle and the triangle gives us an estimate of 7.5 for the total area. When I do my calculation, if I come out with something close to 7.5, I'll think I probably did it right. Now we get the area by integration. This is the definite integral from 1 to 2 of 3x squared dx. The first step is to find the antiderivative, which we found above was x cubed plus c. Then we evaluate it at the upper limit of integration and subtract the same function evaluated at the lower limit, so we get 2 cubed plus c minus the quantity 1 cubed plus c. If we are careful about the parentheses and the signs, we find that the two c's cancel each other out. We're left with 8 minus 1 equals 7. We estimated 7.5, so 7 is close to the estimate and probably correct. 7 plus c would not be correct. The c's have canceled out. They should not be there anymore. In a definite integral, where you have limits of integration, you always subtract, so the c's always cancel out. Because we know they will cancel, we don't need to write them at all. In an indefinite integral, where you don't have limits of integration, There is no subtraction, so the c does not cancel out. It should still be there. That's why you have a plus c in every indefinite integral, but not on a definite integral. Thank you for watching Definite versus Indefinite Integrals by Conceptual Calculus.